Okay, here we are in section 8.3, logarithmic relationships. This is a big section, so you should do what you need to do, stop the video, take some good notes, because this is stuff that's going to come back around. I saw it on the January Regents, so here we go. Okay, let's start. Basic properties of logarithms. And you'll notice that it says here that b is greater than 0, less than 1, or b is greater than 1. And that's because when we come over here and think about our base, for logarithmic functions, we need the b to be greater than 0, so for the domain to work. And if b is 1, 1 to any power is 1, and so that would just be a horizontal line, y equals 1. So you don't necessarily have to get too hung up about this, but just it really has to do with domain issues. Okay, I've tried to kind of put everything in containers that you need to know, but I'll try to help you have ways to remember them. So, and you might not like having these variables, but we have to be general, because this b could be a 10, it could be a 2, it could be a whatever. But hopefully at this point you're pretty clear that anything raised to the 0 power is 1. So now if I come over to the logarithm, means implies. These guys gonna go back and forth between these two things. Once again, a logarithm is an exponent. So a logarithm is an exponent, so that 0 is in this position. The base that we're using here is just a b, and then this 1 is plopping itself over here in this position. So basically, the bottom line is this. The log of 1, doesn't matter what the base is always going to be 0. And if you're starting to feel this is the base when you think about the exponential form. Anything raised to the 0 power is always going to produce a 1. The other part of this is anything, any base raised to the first power is just going to be itself. Doesn't matter what that number is. So going back on my broken record, a logarithm is an exponent. In this case, we have a 1 as our exponent. A logarithm is an exponent. In this case, our base is a b, and we also have a b in this position. So as long as the base and the numbers sitting in this position, it's called the anti-logarithm. It's kind of a yucky word. As long as they match, it's going to be equal to 1. Now these two things you need to know, but I'm here to tell you your calculator will help you with them. So I'm going to come up here, and we're going to talk more about this in a future section, but anytime you hit the log button on your calculator, it's always base 10. So if I put in log 1 and I hit enter, a 0 comes out. So this is a way to remember that the log of 1 is always going to be 0. Now once again, this is only showing me for base 10. So then if I wanted to replicate the second thing I did, where if the base and the number sitting next to the log are the same, I would hit log. Remembering the base is 10, it doesn't come on my screen, but I'm going to put a 10 here. And sure enough, when I hit enter, I get a 1. So it's just a way to maybe get your calculator to help you remember these pieces of information. Okay. So anyway, log of 1, any base is 0. The log, as long as the base and the number sitting next to the log are the same, is going to be 1. So that's one little piece of information. Next up, the beginning of a series of 3 things that you need to know. So basically what you need to know is the thing that I've put in a container here. And you need to know that the log of a product is equal to the log of the factors added together, the sum of the log of the factors. So you'll notice the log of c times d is exactly the same as the log of c plus the log of d. In the end, you just need to know that. If you're curious to know why, I have it on the board over here. And what I've just done over here is I've written an exponential form, b to the x is equal to c, and then I've come over here and written this in logarithmic form. I'm not going to get tangled up in why this is, we've already talked about that. And then I've written just something different, b to the y equals d, and I've written that in logarithmic form. So now, hopefully you remember from the last chapter that when we take two things and multiply, we add the exponents. So if we take c times d multiplying c times d, then what we're doing when we multiply b to the x times b to the y is we add our exponents. And so if you come over here, and I'll say it this time, remember a logarithm is an exponent, so that means a logarithm is an exponent. In this case, the exponent's x plus y. Therefore, that means that the logarithm of c times d is equal to the sum when we add the two logarithms. This actually comes right off the fact that when we multiply powers of the same base, we add the exponents. So it shouldn't surprise you, because remember, logarithm is an exponent, so that when we break this apart, then the log of c times d is the log of c times the log of d. Don't worry too much about these little b's. This is just here to make it very clear that these bases do all need to be the same. Okay. I don't know, just for kicks. Maybe I'll just put this on the board. So say I had something like the log of 10 times 100. Then it is a fact, I'm just doing this to prove this to you, that the log of 10 times 100 has to be the same as the log of 10 plus the log of 100. So the log of 10 times 100 would be the log of 1,000. I'm just going to come back over here to my calculator. Hit clear. So the log of 1,000, if I hit enter, is equal to 3. I'll come back over here and I'll put a 3 here. Put a little question mark here because I'm still in the process of proving this to you. Now we just saw that the log of 10 is 1, but I'll do that again. So when I hit the log of 10, because remember in the case on the calculator, when I hit log, I'm having it was called the common log with a base of 10, and with the 10 in this position and knowing that there really is a little 10 down here, that's going to be equal to 1. So I'll hit enter, and sure enough you can see that. Plus, when I hit log again and throw down 100, so I'm going to hit my log button again, put in 100, and hit enter, and sure enough a 2 comes out. So you can see that, and I just am showing you this because really this is a way that whenever you're questioning yourself, you can always make up a little problem and give it a go and see if you can prove it to yourself that that's a fact. So just to say it one more time, the log of a product, the log of a product, as in two things that are being multiplied, is the sum of the logs of the factors. The sum of the logs of the factors. Plain and simple. Comes in handy when we're sort of pulling things apart. So let's look at an example. So if the log base 5 125 is 3, log base 5 25 is 2, find log base 5 125 times 25. So what good is knowing this fact? Well, we know now then that we could rewrite this. So I can rewrite that as log base 5 125 plus log base 5 25. And from up here, and hopefully your brain is starting to see this anyway, the base of 5, it shouldn't be too surprising because when I take a 5 raised to the third power I get a 25. So in place of this I'm going to put in a 3 plus log base 5 25 is equal to 2. 5 squared is 25. So plus 2. And so when we add 3 plus 2, that's pretty straightforward, is equal to 5. So sometimes when we're given some information, by using these laws, we can pull things apart and find answers a lot easier. Okay, next up, this is what we call the logarithm of quotients. So this is another relationship, and basically it says the following. The logarithm of a quotient, as in when we divide two values, is equal to, now these are fancy words, but it's equal to the log of the dividend minus the log of the divisor. Really, it's the log of the numerator minus the log of the denominator. And in the end, this is for the same reason that when we're taking, because remember, logarithms are exponents, and so if you remember, when we divide powers of the same base, what do we do with our exponents? We subtract. So it parallels it directly. And I basically have shown this over here. Once again, like the y part, you don't have to prove it to me why it is, you just really need to know it. But if you're interested to sort of understand what's going on, you can stop the video for a second and sort of ponder this thought. Okay, so let's put this to work. in an example. Find the log base 5 125 divided by 25. And so I'm going to go off the information that we got in the problem example 1. So I can rewrite this log base 5 125 over 25 has to be the same as log base 5 125 minus log base 5 25. And so from the problem before, from our brains even, because a logarithm is an exponent, so 5, what do we put above a 5 to get a 125? That's a 3. Minus, logarithm is an exponent, what do we put above a 5 to get a 25? A 2. So this has to be equal to 1. Now, in reality, just to review another concept, this is really equal to log base 5 of whatever 125 divided by 25 is, which is 5. And so it shouldn't be too surprising when we have the base and this thing sitting in this position called the anti-log. When they match, it's always going to be 1, which is precisely what we got down here. Okay, one last one for us to think about, and that is the logarithm of powers. So the logarithm of powers basically says that anytime we have a logarithm and whatever is sitting in this position we are raising to the power, it is going to be exactly the same as taking the power times that logarithm. And this actually corresponds to the whole concept, and I have it over here once again just in case you want to understand where this comes from. This has to do with the whole power of a power. And when in using exponents, when we have a power of a power, what do we do but we multiply? So in the end, that's what leads us over to the fact that if necessary, and this comes in handy all the time, you're going to start seeing, if we have the logarithm of some kind of a power, we can rewrite that as the logarithm, or the exponent itself times the logarithm. So let's put this to use here a little bit with a couple more examples. And once again, even if you're kind of confused to begin with here, with practice you're going to be able to do this. I guarantee it. Okay, so given a problem like this, find the log base 2 8 using the product rule. I just want to have you think about it for a minute. Hopefully, and I'm just sort of trying to kind of drill into your head a little bit, that you're starting to realize, like, well, if this is my base, it's a 2, and the logarithm is an exponent, the question really is, what is it I'm going to put above that 2 to produce this 8? And I would hope at this point you see that that would be a 3. But in the end, that's what it's going to equal. But I'm being asked here to use the product rule. So I'm going to go ahead and I'm going to rewrite this. And I'm going to say to myself, well, is there some way I can maybe break this 8 up? And I would suggest that maybe I could do this, and I'll tell you why in a second. Sometimes by breaking something up, like say we don't have a calculator, it's not that easy to figure this out. Now I would say hopefully this is not too difficult to figure out. You can now apply these rules that I'm showing you, where I can rewrite this as log base 2 plus, because remember, when I'm taking this product, I'm going to turn it into adding, plus, once again, log base 2. So, as we learned earlier in this lesson, when these guys match, the number that comes out is a 1. So this is matching, so a 1 comes out, and this is matching 1, so again over here. And so, as we would expect, we get a 3. Okay, another place for this would be something like this. I'm using the same example. Find the log with base 2 8. We already know what the answer is, but this time we're going to use the power rule. So using the power rule, then I'm going to rewrite this, but I'm going to try to rewrite 8 as a power. So, and we've seen 8 a lot since we started talking about exponents, and so 8 is exactly the same as, whoops, I can't lose my logarithm here. So really 8 is the same as 2 to the 3rd power. I'll just put this in parentheses to kind of keep it clean. But we just learned the logarithm of powers, and so what I can do then is I can take this 3 from up above here and pull it down in the front. So this is the same as 3 log base 2 2. And once again, whenever our base and this anti-logarithm match, I can replace that with a 1, getting the exact same answer that we've gotten in the last situation. Okay, 2 more examples. Find log base 12 9 plus log base 12 16. So here's a really good place to start understanding the benefit to these rules. More than likely, your brain is not going to be able to say, well, what exponent do I put above a 12 that produces a 9? What exponent do I put above a 12 that produces a 16? So this is where you say, oh, well, this is just the sum of 2 logs, and yep, they have the same base. So I can rewrite this as a product. And so what's going to start happening here is we need to be able to go back and forth. If we have a sum, we need to make it into a product. If it's a product, sometimes it is beneficial to make it into a sum. So now I have the log base 12 of, turns out that when you take 9 times 16, you get 144. So now if my job is to figure out what this is equal to, it becomes much easier, because when we look at that 12 and say to ourselves, logarithm is an exponent, what exponent is it that we put above a 12 that produces 144? And I think you probably agree with me, that would be a 2. Okay, last example. Sometimes we'll be given problems like this, where we are given some particular logarithm and told that we're going to call it a particular variable. We're given some other logarithm and told we're going to call it a different variable. And this type of a problem is a complete test of our understanding of how to work with these relationships of logarithms. So if we need to take this thing right here and rewrite it in terms of x and y, we need to start breaking it down using these laws that we just met. So I would suggest, when you look at this and you see a quotient, that a starting point might be to say, well, the log of the quotient is the same as the log of the numerator minus the log of the denominator. But at this point, I don't have anything that matches what I've been given up here, so I need to do a little more work with this. So I'm going to go drop down here, and I'm going to say, well, wait a minute. The square root of 3 really is the same as 3 to the half. And I'm going to come over here and I'm going to say, well, wait a minute. If I have 5 squared, that really is the same as 2 times the log base 10 of 5. Now, this is something I can work with because I have the information up here. I'm still not quite there with this other side because I don't have anything with 3 to the half. So I'm going to do the same thing with those power. So I'm going to bring this power 1/2 times log base 10 3, and I'll just rewrite this, minus 2 log base 10 5. So now then I can say, well, I have a match here. I have log base 10 3 and I have log base 10 5, so I can rewrite this as 1/2. Well, log base 10 3 is x minus 2 log base 10 5 is y. So I have now rewritten this thing in terms of x and y, using these relationships that we just went over. Okay, so that is it, your first exposure to these. Don't be afraid. You will work with them and they will make more sense as you practice with them. So it is now your job to go to mathexcelforschools.com and do the quiz and hopefully start getting a sense of how to manipulate logarithms.